The Colosseum rises from the heart of Rome like a monument not only to imperial power, but to human ingenuity itself. To the casual observer, it is simply a massive amphitheater, a stage for gladiators and spectacle. Yet, when one considers the scale of engineering, the precision of construction, and the technological sophistication that made it function, the Colosseum, and the entire Roman civilization, emerges as something far more extraordinary. It was not only a society of conquest and law, but a civilization of systems, processes and technologies that often surpass modern expectations. Rome did not merely build monuments, it created machines, both tangible and conceptual, that allowed an empire to survive, flourish, and awe the world for centuries. Central to the technological genius of Rome was its mastery over water. Water, in the Roman mind, was not simply a resource, it was an instrument of civilization. The aqueducts, some stretching over 50 miles, carried millions of liters of water daily across valleys, hills, and plains. Constructed with meticulous precision, these aqueducts relied solely on gravity, yet flowed with such reliability that water reached even the farthest reaches of Rome with consistent pressure. The gradient of each aqueduct was carefully calculated, often with differences measured in mere centimeters per kilometer. This level of precision ensured smooth, continuous flow, preventing stagnation, overflow, or destruction of the delicate infrastructure. The aqueducts were architectural triumphs as well as functional marvels. With arched bridges carrying channels over valleys, allowing water to move unobstructed across uneven terrain. The Pont du Gard in France and Aqua Claudia in Rome are surviving testimonies to this mastery, demonstrating the seamless integration of form, function, and engineering. The water delivered by these aqueducts was vital not only for drinking but for the functioning of entire cities. Public baths, for instance, were sophisticated spaces engineered for comfort, hygiene, and social interaction. Roman baths or thermae were carefully designed with hot, warm, and cold rooms to manipulate body temperature in precise sequences. The hypocaust system heated floors and walls by channeling hot air from furnaces, maintaining a controlled climate. The walls radiated warmth evenly, the floors remained comfortable to the touch. This was technology applied directly to human physiology. Centuries before modern scientific understanding of heat distribution, thermal comfort, or public hygiene existed, Romans also mastered material science in ways that continue to astonish engineers today. Roman concrete, a mixture of lime, volcanic ash and aggregate, possessed a durability that modern concrete rarely matches. Unlike contemporary cement, which can crack and degrade over decades, Roman concrete grows stronger over time. The chemical reaction between volcanic ash and water creates microscopic crystals within the concrete, reinforcing its structure, a self-healing property that has allowed structures like the Pantheon's massive unreinforced dome to stand for nearly 2,000 years. The precision, experimentation, and empirical knowledge behind these constructions reveal an intuitive mastery of chemistry long before these disciplines existed in formal theory. Road construction was another domain in which Roman technology was unsurpassed. Roads were layered with gravel, sand, cement and stone, designed to provide durability, proper drainage, and load-bearing capacity. Engineers carefully surveyed the terrain, adjusting alignment to maintain stability, avoid flooding, and optimize gradients. Milestones marked distances, ensuring that travelers, messengers, and armies could navigate with precision. Roads were arteries of communication, trade and conquest, connecting distant cities, military forts and ports, enabling the movement of armies and goods with efficiency unmatched by later medieval societies. Some roads, like the Via Appia, remain in use today, more than 2 millennia after their construction, a testament to Roman engineering foresight. Roman technological mastery extended to machinery and industrial processes. Treadwheel cranes allowed workers to lift massive stones for temple construction, bridges, and amphitheaters, multiplying human strength with mechanical advantage. watermills ground grain efficiently to supply cities with bread, one of the staples of the Roman diet. Wine presses and olive oil presses used levers, weights, and hydraulics to extract maximum yield with minimal labor. Even seemingly mundane tools, mills, saws, knives, plows, were carefully designed for durability, ergonomics, and efficiency. Rome industrialized labor through intelligent engineering, automating processes in subtle yet powerful ways. Measurement and information were technologies in their own right. The Romans understood that an empire required not just physical infrastructure but coordinated management. The cursus publicus, Rome's imperial courier system, moved messages across hundreds of miles with astonishing speed. Relay stations, spaced strategically along roads, supplied fresh horses, provisions and rest for messengers, enabling near-continuous transmission of orders and intelligence. Surveying tools like the groma and chorobates allowed engineers to lay out roads, aqueducts, and city grids with mathematical precision. Calendars, censuses, and legal codistrators to manage populations, taxation, military obligations, and public welfare systematically. These information systems were not ancillary, they were the nervous system of the empire, enabling Rome to coordinate millions of people across vast distances. Medicine and public health were similarly technological. Hospitals for soldiers, surgical instruments, and organized sanitation networks minimized injury and disease mortality. Public latrines, sewers and water systems were engineered to reduce contamination, demonstrating a sophisticated understanding of preventive health. Even the timing and construction of public baths reflected the application of thermal engineering and health management. This technological approach to human well-being ensured that cities could sustain dense populations, armies could recover from campaigns, and the empire could endure for centuries. Entertainment, too, was a field of Roman technological innovation. Amphitheaters like the Colosseum incorporated crowd management, acoustics, stage machinery, and elevators for scenery and animals. Chariot races, gladiatorial games, and theatrical spectacles were orchestrated using principles of timing, logistics, and psychology. The architecture itself directed audience movement, distributed sound evenly, and created awe-inspiring experiences, demonstrating that Romans applied engineering not just to survival but to control, comfort, and cultural expression. Underlying all these achievements was a fundamental principle: Roman technology was systemic. Buildings, water, roads, machines, information networks, medicine, and entertainment were interdependent. They functioned together, forming a cohesive framework that supported urban life, military campaigns, economic stability, and social cohesion. The collapse of any one element, say, aqueducts or roads, could disrupt the entire system, highlighting the sophistication of the interlocking network Rome had created. When Rome fell, much of this knowledge regressed. Hypocausts ceased to function. Aqueducts decayed, roads deteriorated, and mechanical processes were forgotten. Medieval societies often lacked even a fraction of the efficiency, hygiene, and reliability Rome had achieved. Centuries would pass before basic principles of engineering, sanitation, and urban planning were rediscovered. Studying Roman technology forces us to reconsider assumptions about human progress. Innovation is not always linear. Some civilizations, like Rome, achieved technological sophistication that modern society still struggles to fully replicate. The genius of Rome lies not only in monumental construction, but in the integration of technical infrastructure, mechanical ingenuity, information systems, and social organization into a coherent, functional, and enduring civilization. The Colosseum, the aqueducts, the roads, and the machines are more than relics. They are evidence of an empire that understood, codified, and applied technology in ways that continue to shock historians and engineers alike. Rome engineered survival, efficiency, and societal cohesion on a scale that remains unparalleled. The empire's physical structures awe us. Its technological systems continue to confound us. And the lessons remain clear: systems, integration, and foresight matter more than brute power alone. Rome succeeded not merely because of its armies, laws, or politics. It succeeded because it engineered civilization itself, through aqueducts, roads, machines, public health, entertainment, and information networks. In every corner of the empire, from city centers to distant forts, the Romans applied technology to control, enhance, and sustain life. This chapter reveals the first, most profound truth: to understand Rome, one must understand its technology, and in doing so, we see a civilization that continues to shock and inspire. More than 2 millennia after its peak. Imagine walking through a Roman insula. The multi-story apartment complexes that house the majority of the population in urban centers. From the outside, these buildings appear functional, even rudimentary. But a closer look reveals deliberate engineering choices. Light, airflow, and waste management were all considered. Courtyards allowed sunlight to reach interior rooms, reducing dampness and promoting health. Ventilation shafts and windows were positioned to facilitate cross breezes, cooling apartments in summer and ensuring that smoke from cooking did not linger. Romans understood the impact of environment on human health long before germ theory existed. Water technology continued inside the home. Wealthier households had private fountains connected to aqueducts, while even modest apartments could access communal fountains. Plumbing was extensive. Ceramic and lead pipes carried water, while drainage systems removed waste. Public latrines, fed by flowing water, were communal yet remarkably hygienic for their time. Sponges on sticks, rinsed in running water, replaced toilet paper, illustrating the Romans' innovative approach to sanitation. Even in crowded urban environments, the combination of aqueduct-fed water, engineered waste systems, and ventilation reduced disease and maintained livability, a feat unparalleled in Europe for centuries after Rome's decline. The kitchen, or cucina, was another space of technological ingenuity. Kitchens were organized for efficiency, with workstations for preparation, cooking and serving. Hearths were positioned to maximize warmth and airflow, while ovens and stoves allowed consistent temperatures. Tools such as knives, grinders, and presses were standardized to facilitate cooking and food processing. Storage vessels, amphorae, and containers were carefully sealed to prevent spoilage, showing an understanding of preservation that predates modern refrigeration. Even small-scale innovations, such as racks for drying herbs or platforms to protect food from pests, reveal a systematic approach to domestic life. Heating extended beyond public baths. Wealthy homes and villas used hypocaust not only in bathing areas but in living spaces. Floors were suspended above empty spaces, allowing hot air from furnaces to circulate beneath and through walls. Rooms were arranged to capture this heat efficiently. Some homes had heated dining rooms, demonstrating that technology was applied to social comfort as well as hygiene. Romans understood the distribution of heat, airflow and energy without thermometers, thermostats, or scientific instruments, relying on empirical observation, experimentation, and iterative improvement. Lighting in Roman homes also reflected thoughtful engineering. Oil lamps provided illumination, but placement and reflective surfaces were used to maximize light while minimizing smoke. Atriums and windows were positioned to capture sunlight, and public streets were lit with torches or oil lamps in strategic locations, improving visibility and safety. In essence, Rome was a city designed for both day and night, with light engineered for function and comfort. Furniture and household tools demonstrate that Roman innovation extended to ergonomics. Beds were raised to prevent pests, chairs were designed for stability, and tables followed predictable dimensions for usability. Storage furniture, cabinets, chests, and shelves, was designed to maximize space. Even portable furniture was constructed with weight distribution in mind, making movement easy and reducing injury. Every domestic object reflected an understanding of physics, materials, and human behavior, turning the home itself into a system of applied technology. Food preservation and preparation were tightly integrated with engineering. Salting, smoking, pickling, and refrigeration using snow or water-cooled cellars were all part of a sophisticated strategy to maintain food quality. Mills ground grain efficiently, while presses for olives and wine applied mechanical advantage to produce consistent results. Food processing was not a casual endeavor, it was mechanized, standardized, and optimized, ensuring that urban populations could be fed reliably. Even the urbanization of streets and neighborhoods was technological. Roads were aligned for drainage, width, and crowd control. Public spaces were positioned to facilitate commerce, governance, and socialization. Markets, forums, and baths were connected to water, roads, and sewage networks, creating a functional urban ecosystem. Cities were not chaotic, they were engineered to handle dense populations, commerce, and the movement of armies and supplies. The psychological impact of these systems cannot be overstated. A Roman citizen experienced order, predictability, and comfort in daily life. Water flowed, streets were maintained, food was accessible, and sanitation was provided. These were technological assurances that reinforced the stability and authority of the state. Technology, of this sense, was as much a social tool as a practical one. Even in less wealthy households, scaled-down versions of these systems existed. Ventilation, water access, and communal sanitation allowed millions to live in relative comfort in cities that could house hundreds of thousands. The knowledge and systems that made this possible were widespread and applied at multiple scales. Rome engineered comfort, hygiene, and efficiency into daily life on a continental scale. Rome's domestic technology also anticipated modern concepts of environmental adaptation. Buildings were oriented to capture sunlight, maximize airflow, and reduce heat gain. Drainage and irrigation managed water for both households and gardens. Noise, light, and airflow were considered in the arrangement of rooms and streets. In essence, the city functioned as a controlled environment, designed to optimize health, efficiency, and productivity, a principle that modern urban planners are still struggling to implement fully. When Rome fell, domestic technology regressed dramatically. Hypocaust became rare, aqueducts fell into disrepair, and sanitation systems collapsed. Medieval Europe would struggle for centuries to rediscover even the most basic principles that Romans applied intuitively. Urban life became harsher, darker, and more perilous. The loss of technological infrastructure directly impacted human health, longevity, and societal stability. Studying these domestic technologies allows us to see the Romans not only as builders of monuments or warriors, but as engineers of everyday life. Kitchens, baths, heating systems, sanitation, lighting, furniture, and street planning were all integrated into a larger system and enabled millions to live in comfort, hygiene, and order. This systemic approach to technology is what allowed Rome to sustain an empire of unparalleled scale and complexity. In examining Roman domestic technology, one begins to understand the full breadth of Roman innovation. It was practical, pure, and deeply human. It touched every aspect of life, from personal comfort to social order. Rome did not merely build for the elite, it built for society as a whole. It did not simply construct infrastructure. It engineered civilization itself. The Roman military was not merely a collection of soldiers, it was a technological marvel, a system where discipline, strategy, and innovation combined to produce an unparalleled force. While historians often focus on the bravery and training of Roman legions, the real shock lies in the technological ingenuity that underpinned their power. From weaponry and armor to siege machines and fortifications, every aspect of Roman military life was engineered with precision, foresight, and efficiency. Understanding this technology reveals how Rome could maintain an empire spanning continents and defend it against threats that would overwhelm lesser civilizations. Consider the armor of a Roman soldier. Lorica segmentata, the iconic segmented armor, was not simply designed for appearance or status. Each plate overlapped with the next, distributing force evenly across the body. Articulated joints allowed for freedom of movement, enabling soldiers to fight with agility while remaining protected. Helmets were crafted to protect the skull and face without obstructing vision or hearing, incorporating flanges, cheek guards, and neck protection. Even shields, standardized in size and weight, were engineered for both defense and tactical formation. The scutum allowed soldiers to form the impenetrable testudo, a human shield that could withstand volleys of arrows, stones, or other projectiles. Every element of military gear reflected understanding of mechanics, ergonomics, and battlefield requirements. Weapons, too, were products of applied science. Pilum, the heavy javelin, was designed with a soft iron shank that bent upon impact, preventing enemies from throwing it back and disabling shields. Swords were balanced for thrusting and slashing, and spears were engineered for maximum penetration with minimal effort. Even siege weapons were astonishingly sophisticated. Ballistae, powered by torsion springs, could hurl massive bolts with precision over long distances. Onagers converted rotational energy into devastating kinetic force, capable of breaching walls or decimating formations. Engineers calculated angles, weights, and tension to optimize damage while preserving the durability of the machines themselves. Every siege was not chaotic. It was the application of physics and mechanical insight to achieve predictable results. Fortifications were another domain where Roman technology excelled. City walls were layered with stone and brick, designed to absorb impact and resist erosion. Towers punctuated these walls, providing vantage points and fields of fire. Gates incorporated mechanical locks and defensive mechanisms to trap or repel intruders. Temporary military camps, or castra, were engineered with astonishing precision. Built in a single day during campaigns, they followed standardized layouts with defensive ditches, palisades, streets, and strategically placed command posts. Even in temporary constructions, Romans applied principles of geometry, weight distribution, to protect soldiers and resources. Engineering extended to the battlefield itself. Roman generals considered terrain as both obstacle and advantage. Hills, rivers, forests, and marshes were analyzed and adapted to create defensive positions or launch offensives. Pontoon bridges allowed armies to cross rivers quickly, while modular fortifications could be erected in minutes. Knowledge of hydrology, soil stability, and slope was applied to enhance strategic advantage. Warfare was thus transformed from random violence into a predictable and controllable system, where technology magnified the effectiveness of manpower and discipline. Communication on the battlefield was equally advanced. Signal towers, flags, torches, and pre-arranged codes transmitted messages across distances that would otherwise have been impossible to cover quickly. Generals could coordinate multiple legions, cavalry, and support units with a level of precision that kept enemies off balance. The Roman army treated information as a weapon, understanding that speed, reliability, and accuracy could be as decisive as strength or courage. Naval warfare, too, showcased Roman innovation. Ships were engineered for stability, speed, and offensive capability. Triremes and quinquiremes utilized multiple rows of oars, coordinated in rhythm to maximize propulsion. Hulls were reinforced to withstand ramming maneuvers, and boarding equipment allowed soldiers to capture enemy vessels. Harbors, quays, and cranes were integrated with logistics systems, enabling rapid loading and deployment. Control of the Mediterranean was not a matter of chance. It was the result of coordinated technology, strategic design, and disciplined implementation. Logistics were inseparable from military technology. Armies required continuous supply of food, weapons, and equipment. Roman roads, bridges, and depots ensured that legions remained operational even far from their home provinces. Mobile workshops and siege units allowed the construction and maintenance of equipment on the move. Engineers calculated load distribution, transport efficiency, and resource allocation, creating a system in which armies could sustain themselves over months or years of campaigning. Rome effectively mechanized the flow of human and material resources, a level of organization that would not be matched until modern industrialized warfare. The psychological impact of Roman military technology was profound. Fortified camps, disciplined formations, siege engines, and armored soldiers projected inevitability and power even before battle began. Enemies often surrendered not because they were outnumbered, but because they faced machines and systems designed to neutralize resistance efficiently. Technology became both shield and sword, controlling not only physical outcomes but morale and perception. After the fall of Rome, much of this military technology regressed. Fortifications fell into disrepair. Siegecraft knowledge dissipated, standardized equipment became rare, and logistical expertise was lost. Armies became reliant on sheer manpower rather than engineering, and it would take centuries to regain even rudimentary aspects of Roman innovation. Studying Roman military technology today forces us to confront the scale, precision, and integration of systems that allowed a civilization to dominate across continents for centuries. It reminds us that power alone is insufficient. The application of knowledge, design, and mechanical insight is what sustains empire. Roman military technology was holistic. Armor, weapons, fortifications, siege engines, bridges, ships, logistics, and communication were not isolated inventions. They were part of an interconnected system that multiplied effectiveness and resilience. A single legion was thus more than soldiers with weapons. It was a self-sustaining, highly engineered unit capable of projecting influence across vast distances. The combination of observation, experimentation, mechanical insight, and coordination transformed warfare into an engineered discipline, something far ahead of its time. In essence, the Roman army was not merely a fighting force. It was a demonstration of technological integration, applied intelligence, and human organization. It represented the culmination of centuries of experimentation, observation, and refinement. Every spear, shield, wall, and catapult was part of a larger system that optimized efficiency, safety, and effectiveness. By examining these achievements, one realizes that Roman technology was not confined to monuments or roads. It extended into very mechanics of survival, conflict, and societal stability. Rome's legions were not simply armed men, they were living embodiments of applied engineering, moving systems, and technological mastery. Rome's mastery of technology extended far beyond weapons and fortifications. To govern an empire spanning continents, the Romans understood that infrastructure, transport, and logistics were as crucial as armies and laws. Movement was the lifeblood of the empire. The ability to transport armies, goods, and information with speed and reliability defined the difference between survival and collapse. Roman engineers created transportation system vehicles and maritime technologies that continue to astonish modern observers, revealing a civilization that approached logistics with precision, foresight, and innovation. Roads were the foundation of Roman mobility. The Via Appia, often called the Queen of Roads, was more than a path of stone. It was a carefully engineered conduit, layered to endure centuries of use and weather. Gravel, cement, sand, and carefully cut stones formed stratified layers that provided drainage, stability, and resilience. Roads were surveyed to follow gradients that allowed efficient movement while minimizing erosion and flooding. Curbs, milestones, and drainage ditches complemented the road surface, creating not just a path, but an integrated system of transportation infrastructure. Roads were arteries of commerce, communication, and military operations, allowing Rome to project power and sustain its economy across vast distances. The vehicles that traversed these roads were equally engineered. Carts, wagons, and chariots were standardized in size and axle width to maintain balance and prevent accidents. Wheel hubs reduced friction, often lubricated with olive oil, and multiple axles distributed weight evenly for heavy loads. Pack animals, horses, mules and oxen, were integrated into the system with careful attention to terrain, load, and endurance. Saddles, harnesses, and yokes were designed to maximize efficiency and minimize injury. These transport technologies did not exist in isolation. They formed an interconnected network with roads, bridges and depots to enable seamless movement across the empire. Bridges exemplified Roman engineering mastery. Stone arches, often spanning valleys and rivers, distributed weight efficiently, allowing both light carts and heavy military equipment to cross safely. Bridges were built with consideration for water flow, using cutwaters and piers to minimize erosion. In some cases, temporary wooden structures could be erected within days to support advancing armies, demonstrating adaptability as well as permanence. Every bridge was not only a conduit but a calculated response to environmental challenges, integrating material science, hydrology, and structural engineering into functional infrastructure. Maritime technology extended Rome's reach beyond land. Ships were engineered for cargo, speed, and combat. Merchant vessels transported amphorae filled with olive oil, wine, grain, and luxury goods across the Mediterranean. Hulls were shaped for stability. Keels reduced the risk of capsizing, and sails captured wind efficiently, while oars provided maneuverability in calm waters and crowded ports. Naval warfare vessels, from triremes to quinquiremes, were designed with reinforced hulls for ramming, multiple rows of oars for speed, and boarding equipment for combat. Maritime technology was integrated with ports, docks, warehouses, and quays, forming logistical hubs that enabled trade, resupply, and military operations across vast distances. Ports were technological centers in their own right. Docks were constructed for durability, cranes lifted heavy cargo, and storage facilities, or horia, maintained products in controlled environments. Access channels were dredged and water flow was managed to facilitate ship movement. These systems allowed Rome to supply cities thousands of kilometers from production centers reliably. Maritime and land transport were integrated, demonstrating that Rome understood logistics as a multidimensional challenge, engineered, coordinated, and maintained systematically. River transport complemented roads and maritime routes. Shallow, draft boats carried bulk along the Tiber, Rhine and Danube, supported by locks, canals, and weirs to control water levels and navigation. Hydraulic engineering enabled reliable movement even in variable conditions. The combination of roads, rivers, and ports formed a transportation network that connected cities, production centers, and military forts, allowing rapid deployment of troops, resources, and information. Storage and inventory were also engineered. Grain, olive oil, wine, and other perishables were stored in fortified warehouses with regulated airflow, temperature control, and security. Standardized containers allowed accurate tracking and distribution across provinces. The ability to store and move resources efficiently enabled the empire to respond to disasters, supply armies, and maintain urban populations without interruption. Logistics was not secondary, it was a core technology of governance. The Roman military relied heavily on this transportation network. Supply trains moved food, weapons, and equipment with precision. Fortifications were often constructed near supply roads, ensuring that armies could operate far from home without risk of starvation or equipment failure. Roads, bridges, ports, and rivers formed an integrated system that allowed rapid response to threats, enabling Rome to dominate both strategically and tactically. Military technology was inseparable from infrastructure. The empire was a machine in which movement, supply and combat were synchronized. This technological mastery had profound psychological effects. Citizens trusted that supplies would arrive, armies would respond, and governance would function efficiently. The predictability of transportation systems reinforced the authority of the state. Technology, in this sense, was both practical and symbolic. It demonstrated control over nature, distance, and human effort. After the fall of Rome, much of this infrastructure decayed. Roads crumbled, bridges collapsed, ports silted, and navigational knowledge fragmented. The collapse of transportation technology contributed directly to the instability of medieval Europe, with travel becoming slow, trade risky, and armies unable to respond efficiently. The loss of these systems illustrates how critical technology is not only for economic prosperity, but for social and political stability. Roman transportation technology continues to influence modern engineering. Road layering techniques, bridge construction principles, and logistical organization echo in contemporary systems. Ports, cranes, and warehouses owe a conceptual debt to Roman planning. What shocks historians is not merely the scale of Roman achievement, but the integration, foresight, and reliability of their systems, designed for efficiency, durability, and predictability in a world without modern machinery, engines, or electricity. The empire's technological mastery of movement, across land, rivers, and seas, enabled Rome to feed cities, mobilize armies, coordinate governments, and maintain a complex society across thousands of kilometers. Roads were not just stone. They were instruments of power. Ships were not just vessels, they were extensions of the empire's reach. Bridges were not merely structures. They were tools that enabled control and influence. Every element of transportation was interlinked, forming a living system that amplified Roman capability far beyond what mere manpower or wealth could achieve alone. Studying Roman transport technology reveals a civilization that thought in systems, optimized for resilience, and understood the cascading effects of movement and logistics. Rome did not merely move goods or armies, it engineered the flow of life itself. Roads, rivers, ports, ships, carts, bridges, and warehouses were all part of a network designed for continuity, efficiency, and control. It is this integration, more than any single invention, that shocks modern observers and cements Rome's legacy as a civilization of technological mastery. Rome's power was not simply in its armies or infrastructure. It was in its ability to manage resources across a vast empire. The logistics of supply and distribution were as critical to Roman dominance as roads, bridges, or ships. Cities with hundreds of thousands of inhabitants, armies stationed thousands of miles from the capital, and distant provinces all relied on a carefully engineered network of resources. Rome understood that to sustain empire, food, materials, and essentials had to flow predictably, efficiently, and reliably. This system of resource management was in many ways one of the most advanced technological achievements of the ancient world. Grain, the staple of Roman life, demonstrates the sophistication of this system. The annona, or grain supply, was meticulously calculated to feed the populace of Rome. Harvested crops from Egypt, Sicily, North Africa, and Gaul were transported via ships, stored in granaries, and distributed according to demand. Granaries, or horia, were engineered for durability, ventilation, and protection from pests. Elevated floors allowed airflow to reduce moisture. Thick walls insulated against heat and cold, and standardized containers facilitated counting, measurement, and allocation. Even small errors in storage or distribution could trigger famine, so precision was critical. Roman engineers, bureaucrats, and administrators collaborated to maintain a system that sustained a city of over 1 million people. Transporting grain required careful coordination. Ships, equipped with standardized cargo holds, carried bulk loads across the Mediterranean. Harbors were engineered for loading and unloading efficiency, often with cranes and ramps to handle heavy amphorae. Roads and river networks extended this reach inland, connecting granaries to marketplaces and bakeries. The empire's supply chains were monitored, with officials ensuring schedules were maintained, losses minimized, and quality preserved. Resource management was thus a technological endeavor as much as an administrative one, integrating materials science, engineering, and logistics into a single cohesive system. Storage of other essential commodities followed similar principles. Olive oil, wine, textiles, metals, and luxury goods were all housed in purpose-built facilities. Amphorae, barrels, and crates were standardized for volume and shape, allowing predictable stacking. Transportation and distribution. Warehouses were placed strategically near ports, roads and cities, ensuring goods could be moved efficiently to where they were needed. Storage technology combined knowledge of materials, climate, and physics, producing facilities that could preserve goods for months or years. The Roman military depended heavily on these systems. Armies on campaign required constant supplies of food, water, weapons, and equipment. Mobile depots, fortified supply lines, and temporary storage facilities ensured legions could operate far from permanent bases. Engineers calculated load capacities, transport times, and resupply intervals, creating a system where military operations could be sustained over months or even years. This integration of logistics with engineering amplified Rome's military power, allowing it to project force across vast distances with precision and reliability. Urban supply networks were similarly sophisticated. Markets were organized to allow smooth distribution of food, goods and services. Streets were designed for both pedestrian and vehicular traffic, allowing carts and pack animals to reach central marketplaces efficiently. Inspectors monitored quality, weights, and measures to maintain fairness and prevent corruption. Water and waste systems were connected to markets, public baths, and kitchens, ensuring hygiene and reducing the spread of disease. The city functioned as an engineered organism, with supply chains, infrastructure, and administration working together to sustain life and social order. Romans also understood the psychological and political importance of resource management. The distribution of grain, or annona, was not merely a matter of survival, it reinforced loyalty, stability, and the authority of the state. Free or subsidized grain for citizens was both a technological and social system, combining agriculture, transport, storage, and administration into a tool of governance. The empire's stability depended not just on armies or laws, but on predictable flows of essential resources to millions of people. Resource management was not static. Seasonal variations, harvest fluctuations, and military campaigns required constant adjustment. Officials monitored weather, crop yields, and storage levels, making calculations to redistribute supplies as needed. Contingency planning was built into the system, with reserves, emergency shipments, and alternate routes ensuring that disruptions did not lead to collapse. This adaptability was a hallmark of Roman technological foresight, allowing the empire to sustain itself in the face of unpredictable challenges. Engineering principles extended to food processing as well. Mills ground grain with water or animal power, producing consistent flour for bread, the staple of Roman diets. Wine presses and olive oil presses applied mechanical advantage to maximize yield and minimize labor. These processes were standardized, repeatable, and scalable, allowing mass production to feed cities, armies, and markets efficiently. Even culinary tools, storage vessels, and kitchen layouts were optimized for productivity, reflecting an attention to system-wide efficiency that would not be seen again for centuries. After the fall of Rome, much of this technological knowledge was lost. Granaries decayed, roads deteriorated, and the sophisticated management of resources collapsed. Cities faced scarcity, armies struggled with supply, and long-distance trade faltered. The decline illustrates the critical role of technology, not just in construction or warfare, but in the very sustenance and survival of society. Civilizations rise and fall not merely because of power or politics, but because of their ability to manage resources effectively, a lesson exemplified by Rome. By studying these systems, one realizes that Roman technology was more than monuments, aqueducts, or roads. It encompassed planning, organization, materials, transportation, and human behavior in an integrated framework. Grain silos, amphorae warehouses, and supply routes were all part of a living system designed to sustain life on an unprecedented scale. The empire's ability to feed, clothe, and supply millions over continents and decades was a technological achievement as remarkable as the Pantheon's dome or the Colosseum's arches. In essence, Rome engineered not just structures or weapons, but civilization itself. Supply chains, storage, transport, and resource management were designed, tested, and optimized to function seamlessly across thousands of kilometers. These systems multiplied human effort, reduced risk, and created predictability, allowing millions to live, work, and fight within a coherent societal framework. The empire's technological mastery was systemic, integrated, and enduring, demonstrating that Rome's greatest innovation may have been its ability to sustain itself, over time and space, through applied engineering, foresight, and organization. Rome's cities were not just centers of administration, commerce, and culture, they were meticulously engineered ecosystems, designed to support dense populations with efficiency, hygiene, and comfort that often surprises modern observers. While much attention is given to monumental structures, the Colosseum, the Pantheon, the aqueducts, the real technological marvel of Roman urbanism lay in its attention to daily life, urban planning, and the integration of multiple systems into a functioning whole. Streets, drainage, water supply, lighting, markets, and residential layouts were all part of a coordinated framework that allowed cities to function smoothly. Even under the pressure of hundreds of thousands of inhabitants, Roman streets were carefully constructed, with layered foundations that ensured durability and drainage. Cobbled surfaces, sometimes crowned to allow water runoff, reduced flooding and maintained navigability in all seasons. Curbs separated pedestrian paths from vehicular traffic, while sidewalks and stepping stones allowed citizens to cross streets safely during rain or flooding. Streets were more than conduits, they were designed to regulate flow, prevent congestion, and integrate with the broader city grid. The alignment of streets often followed geometric principles, demonstrating a deliberate approach to urban planning rather than ad hoc development. Drainage was central to urban design. Sewer systems such as the Cloaca Maxima in Rome removed waste from streets and homes, directing it into rivers or treatment areas. Public latrines were connected to flowing water, minimizing health hazards. Stormwater was managed with channels and culverts, ensuring that heavy rains did not paralyze the city. This attention to water management was both practical and technological, protecting infrastructure, maintaining sanitation, and enhancing public health. Rome's engineers understood the importance of integrated drainage long before the development of modern urban engineering. Public water access extended beyond aqueduct-fed fountains to baths, private homes, and cisterns. Bathhouses were not merely recreational, they were technological wonders, featuring HEPA heating systems, controlled water flow, and sophisticated plumbing. Furnaces generated hot air, circulated beneath raised floors and through walls, creating evenly heated rooms. Pools were designed with precise gradients to maintain temperature, and complex valve systems controlled the flow of water. Bathhouses served hygiene, socialization, and relaxation, but they were also demonstrations of engineering applied to human comfort. Markets were carefully positioned and designed to maximize efficiency. Vendors had designated spaces, storage facilities were nearby, and roads facilitated the transport of goods. Warehouses stored excess stock, protected by architecture that controlled temperature, humidity, and pest access. Inspectors monitored quality, ensuring standard weights, measures, and product integrity. The marketplace was both an economic hub and a controlled system, engineered to maintain the flow of goods, regulate commerce, and minimize waste or spoilage. Roman citizens could rely on markets for predictable access to food, materials, and essential products, a reliability that reinforced social stability. Residential areas displayed technological ingenuity at every scale. Wealthy homes were designed with atriums, courtyards, and ventilation shafts to manage light airflow and temperature. Insulae, the multi-story apartment blocks housing most urban populations, integrated courtyards and shafts to prevent stagnation and distribute sunlight, improving livability despite dense occupancy. Kitchens, hearths, and water access were carefully planned, reflecting an understanding of efficiency and hygiene. Even storage for food, clothing, and personal items was engineered to minimize spoilage and optimize space. Residential design was both functional and adaptive, responding to environmental conditions, social needs, and health considerations. Lighting in the city was another technological consideration. Oil lamps illuminated streets, public buildings and homes, while reflective surfaces and architectural features maximized the distribution of light. Public areas were illuminated strategically to enhance safety, facilitate commerce, and enable evening social interaction. Romans understood that controlling light was essential for security, productivity, and urban experience, and they applied technology to achieve these ends despite the limitations of their time. Urban planning also accounted for transportation. Roads, bridges, and thoroughfares connected markets, public buildings, military installations, and residences. Carts and pack animals moved along designated routes, while traffic regulations and milestones helped maintain order. The integration of pedestrian vehicular and water transport systems minimized conflict and maximized efficiency. Rome's streets were not merely paths. They were controlled systems that orchestrated the movement of people, goods, and information throughout the city. Sanitation and public health were technological priorities. Waste management systems, combined with aqueduct-fed water and HEPA heating, reduced disease prevalence and improved quality of life. Public latrines and baths were maintained as communal resources, with running water and drainage to prevent contamination. The integration of these systems demonstrated a sophisticated understanding of hygiene and public health, anticipating many principles of modern sanitation engineering by centuries. The psychological impact of this technological integration cannot be understated. Citizens experienced daily life in a city that appeared orderly, predictable, and functional. Streets drained efficiently, water flowed reliably, food was accessible, and sanitation reduced exposure to disease. This predictability reinforced trust in civic administration, enhanced social cohesion, and strengthened the perception of imperial control. Technology in Rome was not merely functional, it was a tool of governance, maintaining stability through design and engineering. After the collapse of the Roman Empire, much of this urban technology was lost. Sewer systems deteriorated, roads fell into disrepair, and the carefully engineered integration of streets, markets, and residential areas disintegrated. Cities became more chaotic, less hygienic, and harder to sustain, illustrating the importance of systemic technological planning in maintaining civilization. Medieval urban centers struggled to replicate even the basic functionality of Roman urbanism, often regressing into overcrowded, unsanitary, and poorly connected settlements. Studying Roman urban technology reveals a civilization that applied engineering principles to everyday life on a grand scale. Streets, drainage, water, lighting, markets, and housing were not isolated innovations, they were interdependent systems that collectively created livable, efficient, and resilient cities. Romans understood that the effectiveness of civilization depended on the integration of multiple technologies: mechanical, hydraulic, architectural, and organizational, into a cohesive whole. In essence, Roman urban planning and technology transformed cities into living machines, orchestrated environments where human activity, commerce, and governance could operate smoothly. The combination of engineering, material science, environmental understanding, and social organization allowed Rome to maintain urban centers that were not only functional but were notably sophisticated, even by modern standards. The shock of realizing this lies in the fact that these achievements were accomplished through modern machinery, or computational tools, yet they remain relevant lessons in integrated design and systemic thinking. The study of Rome's urban technology demonstrates that its genius was not merely in monumental structures or military conquests, but in the seamless integration of systems that made life manageable, predictable, and sustainable for millions. Cities functioned as coordinated organisms where roads, water, sanitation, commerce, and housing were engineered to work together. In this way, Rome's urban technology was a silent yet powerful instrument of civilization, sustaining life, reinforcing authority, and enabling an empire to thrive across time and space. Rome's architectural achievements were more than monuments to power. They were demonstrations of technology, innovation, and engineering mastery. While structures like the Colosseum, aqueducts, and Pantheon attract awe for their scale and beauty, the underlying principles that allowed them to stand for millennia reveal a civilization deeply attuned to materials, forces, and design. Roman architecture was not merely aesthetic, it was functional, durable, and often revolutionary, blending artistry with applied science in ways that continue to astonish modern engineers. Concrete was the backbone of Roman architectural innovation. Unlike modern cement, Roman concrete combined lime with volcanic ash, creating a material that grew stronger over time rather than weaker. This unique composition allowed massive structures, such as the Pantheon's unreinforced dome, to resist gravity, weather, and the passage of centuries. The secret lay in the chemical reaction between volcanic ash and lime when exposed to water, producing tiny crystals that reinforce the concrete. Engineers experimented with proportions, aggregates, and curing methods to achieve the desired strength and durability. Unlike brick or stone, which were limited by size and weight, concrete allowed Romans to create fluid, expansive flow previously impossible in architecture. Arches and vaults exemplify Rome's mastery of structural engineering. Arches distributed weight efficiently, transferring loads to supporting columns or walls while allowing open interior spaces. The vault, an extension of the arch, enabled ceilings to span large areas without intermediary supports, creating expansive halls, corridors, and public spaces. Barrel vaults, groin vaults, and ribbed constructions were employed strategically, depending on function and scale. These innovations allowed Romans to construct baths, basilicas, and amphitheaters that could accommodate tens of thousands of people safely. Every arch and vault reflected careful calculation, empirical observation, and a deep understanding of material properties and load distribution. Domes represented the pinnacle of Roman architectural ingenuity. The Pantheon, with its massive hemispherical dome, remains one of the largest unreinforced concrete domes in the world. Engineers reduced weight at the apex by incorporating lighter materials, such as pumice, and used coffering to minimize mass while maintaining strength. The oculus at the center not only reduced structural load, but served as a source of light and symbolic connection between the heavens and human ingenuity. Constructing such a dome required meticulous planning, scaffolding, and coordination, demonstrating that Roman architecture was as much about project management and engineering as it was about aesthetics. Public buildings integrated functionality with technology. Bath complexes required precise control of water flow, temperature, and heating, using hypocaust systems and aqueduct-fed plumbing. Amphitheaters incorporated complex systems for crowd management, acoustics, and stage machinery. Markets and basilicas were designed for both commerce and public assembly, with careful attention to lighting, airflow, and circulation. Even temples reflected engineering principles. Columns were proportioned to support roofs, while staircases were designed for stability, and stonework was aligned with precision to ensure longevity. Architecture was not merely visual, it was a technology designed to solve structural and functional challenges. Roads, bridges, and aqueducts were architectural as well as engineering achievements. The precision of survey, gradient, and construction techniques required mathematical insight, craftsmanship, and labor coordination. Bridges employed arches and piers designed to resist both static and dynamic loads. Aqueducts maintained gentle slopes over long distances to ensure consistent water flow. Each structure was a system, integrating materials, design, and environmental conditions to achieve predictable outcomes. Romans treated construction as a science, experimenting, iterating, and refining techniques over centuries. Urban planning was closely tied to architecture. Forums, squares, temples, and public buildings were arranged to facilitate movement, visibility, and social interaction. Streets and residential blocks were aligned for sunlight, airflow, and accessibility. Drainage and water supply systems were integrated seamlessly into the cityscape. Architectural decisions were therefore part of a larger systemic understanding of urban life, demonstrating that Romans did not view structures in isolation. They were components of a coordinated civic organism. Housing ranged from monumental villas to insulae, the densely packed apartment blocks. Even insulae, often criticized for their height and risk of collapse, were engineered with foundations, walls, and layouts designed to maximize stability and light. Staircases, corridors, courtyards, and ventilation shafts were integrated to improve habitability despite dense occupancy. Wealthier homes incorporated atriums, peristyles, and private baths, while practical innovations, raised floors, drainage systems, and storage solutions, enhanced comfort and safety. Residential architecture reflected a blend of social hierarchy, function, and technological insight. Roman architecture also anticipated modern environmental design. Orientation of buildings considered sun angles and wind patterns. Materials were chosen for thermal properties, durability, and load-bearing capacity. Water, heat, and airflow were managed with engineering solutions, creating indoor environments that remained comfortable without modern HVAC systems. Romans effectively applied principles of passive heating, ventilation, and natural lighting centuries before these concepts became codified in architectural science. Decorative elements often had functional purposes. Columns, cornices, and moldings enhanced structural stability. Marble cladding and plaster protected walls from weather and wear. Domes and vaults used coffering to reduce weight while preserving strength. Even mosaics and floor patterns contributed to thermal regulation and water drainage. Ornamentation was integrated with engineering, demonstrating that Roman architects considered aesthetics and functionality simultaneously. The shock of Roman architecture lies not merely in surviving monuments, but in the systemic integration of knowledge, materials, and design. Buildings were engineered for durability, adaptability, and human use, reflecting centuries of accumulated empirical wisdom. Unlike civilizations that focused solely on aesthetics or symbolism, Rome applied technological insight to create structures that served multiple purposes: functional, social, symbolic, and administrative. After the fall of Rome, many architectural techniques were lost or simplified. Massive domes, complex vaults, and integrated urban planning largely disappeared in Europe until the Renaissance. The decline illustrates that Roman architecture was not just about construction. It embodied technical knowledge, project management, and systemic engineering that were difficult to replicate without the societal infrastructure to support them. Modern engineers and historians still study Roman construction to understand materials, methods, and project coordination, acknowledging that the Romans achieved feats unmatched in many ways even today. Roman architecture therefore was a testament to applied technology. Concrete arches, vaults, domes, plumbing, urban design, and environmental adaptation collectively represent a civilization capable of solving complex engineering challenges with precision, foresight, and ingenuity. These achievements were not incidental, they were the result of deliberate experimentation, systemic thinking, and the integration of multiple disciplines into coherent, functional, and enduring structures. By examining Roman architecture, one realizes that the empire's genius lay not only in monumental aesthetics, but in the seamless fusion of art, science, and technology. Structures were simultaneously functional, durable, and visually compelling. They addressed structural challenges, environmental conditions, and human needs in ways that remain instructive and inspirational. The legacy of Roman architecture is thus both practical and conceptual. It shocks modern observers with its scale, durability, and sophistication, and it offers timeless lessons in the integration of technology, design, and human purpose. Rome's mastery of technology extended far beyond concrete, arches, and roads. It penetrated the fabric of daily life, commerce, and industry. While monumental structures and military prowess often dominate discussions of Roman innovation, the empire's economic and industrial systems were equally sophisticated, showcasing applied technology that fueled the growth, stability, and resilience of a civilization spanning continents. From workshops and mills to mining, metallurgy, and craft production, the Romans developed processes and machinery that were precise, efficient, and scalable. Long before the Industrial Revolution would replicate similar methods, Roman mills, for example, were technological marvels of automation and mechanical advantage. Grain, the cornerstone of the Roman diet, had to be processed efficiently to feed millions in cities and armies across the empire. Watermills harnessed the kinetic energy of rivers and streams, converting it through vertical or horizontal wheels into rotational power that turned millstones. These mills allowed flour to be ground on a scale impossible with manual labor alone. Engineers designed gears, shafts, and bearings to maximize efficiency, reduce friction, and ensure durability. The Romans even experimented with multi-story mills, where grain moved through multiple grinding stages using gravity, conveyor chutes, and water power, a system strikingly similar to modern industrial workflows. Oil and wine production also reflected a deep understanding of mechanics and materials. Olive presses and wine presses employed levers, screw mechanisms, and weights to extract maximum yield from raw materials. Pressing vats were designed to optimize pressure distribution, while channels, pipes, and spouts directed liquid efficiently into storage containers. These processes were standardized across workshops, enabling consistent quality, predictable yields and large-scale distribution. Such mechanization minimized human labor, preserved resources, and ensured that urban populations and armies could rely on a steady supply of essential commodities. Metalworking and mining were equally sophisticated. Romans extracted iron, copper, lead, tin, gold and silver from mines that employed advanced engineering techniques to access ore deep underground. Drainage systems prevented flooding, shafts were reinforced with timber, and ventilation allowed miners to work safely in confined spaces. Smelting and forging techniques were refined for both efficiency and quality. Iron tools and weapons, bronze statues, coins, and fittings all required careful temperature control, knowledge of alloys, and precise craftsmanship. Roman metallurgy was integrated with logistics, ensuring raw materials were transported to workshops, processed efficiently, and distributed to consumers, armies and government institutions. Textiles and craft industries similarly leveraged technology. Wool, flax, and silk were spun, woven, dyed, and finished using standardized looms, spindles, and dyeing vats. Workshops were organized to maximize labor efficiency, with materials flowing from preparation to distribution in predictable sequences. Leatherworking, pottery, glassmaking, and woodworking all incorporated specialized tools and processes designed to improve productivity and consistency. Roman craftsmen were not merely artisans, they were engineers of materials and processes, applying empirical knowledge to maximize output while maintaining quality. Roman commerce relied heavily on this industrial technology. Markets, warehouses, ports, and roads formed integrated supply chains that connected producers with consumers, both locally and across the empire. Standardized containers, amphorae, barrels, crates enabled predictable transport, stacking and storage. Measurement systems ensured consistency in weights and volumes, facilitating trade, taxation and pricing. Even packaging and labeling reflected technological thinking, optimizing handling, protection from spoilage and transport efficiency. The empire's economic vitality depended not just on production, but on the orchestration of a complex network of industrial, transportation, and administrative systems. Water and hydraulic technology were critical to industrial production. Watermills powered not only grain grinding but sawmills, fulling mills for textiles, and hammers for forging metals. Engineers calculated flow rates, wheel diameters, and gearing ratios to maximize energy output. Channel sluices and reservoirs managed water supply, ensuring operations could continue reliably even during dry seasons. Hydraulic innovation extended beyond mills, fountains, baths, irrigation systems, and public latrines all relied on precise control of water movement, demonstrating a comprehensive approach to liquid management that combined utility, efficiency, and engineering foresight. Standardization was a hallmark of Roman industrial technology. Workshops produced tools, coins, pottery, and other goods according to consistent dimensions, weights, and quality standards. Standardization allowed interchangeable parts, predictable outcomes, and scalability. Military equipment, construction materials, and household items could be replicated, efficing errors and waste. This principle extended to administration. Supply chains, tax collection, and resource allocation were designed with the same attention to repeatable processes and measurable outputs, making the empire not just large but systematically manageable. Transportation was deeply integrated with production. Goods produced in mines, workshops, and farms were transported via roads, rivers, and maritime routes to cities and military outposts. Loading, storage, and inventory were carefully calculated to minimize damage, optimize space, and ensure timely delivery. Ports, warehouses, and carts were designed to work together as part of a larger network, enabling movement on scales that would stagger modern observers. Logistics, transport, and production formed a seamless system, transforming the empire into a living machine powered by technology, coordination, and human ingenuity. The social and political impact of industrial technology was profound. Reliable production and distribution ensured urban populations were fed, armies were supplied, and public works were maintained. Citizens experienced stability, predictability, and security, reinforcing loyalty to the state. Technological mastery of production and logistics was thus inseparable from governance and social cohesion. Rome's ability to engineer economic life on a massive scale was as critical to its survival as its military campaigns or monumental architecture. After the fall of Rome, much of this industrial knowledge regressed. Watermills fell into disrepair, workshops closed, and mining techniques were lost or simplified. Standardization disappeared, and supply chains fragmented, contributing to the economic and social instability of medieval Europe. The decline underscores the critical role of technology in sustaining complex societies, not merely as tools for convenience, but as foundational systems enabling urban life, commerce, and military capability. Roman industrial technology shocks modern observers, modernly in scale but in integration, foresight, and efficiency. Mills, presses, workshops, mines, ports, and supply chains formed a network that sustained life, power, and wealth across an empire spanning continent. Engineering was not isolated to structures or weapons, it was applied to food, materials, labor, and logistics. Romans built systems that multiplied human effort, reduced risk, and enabled predictable outcomes, a level of technological sophistication that would not be replicated for over a millennium. By examining Roman industry, one realizes that the empire's true genius lay in systemic thinking. Production, transport, storage, and administration were designed to work together as a cohesive whole. Materials were transformed, goods were moved, and labor was coordinated in ways that maximized efficiency and minimized error. Technology was not merely additive. It was integrative, connecting multiple domains into functional networks that sustained an empire for centuries. The legacy of Roman industrial and economic technology is both practical and conceptual. It demonstrates the power of systematic engineering applied to production, logistics, and urban life. It shocks us because it reveals a civilization capable of operating at scales, precision, and efficiency that many would assume were impossible without modern machines. The Romans achieved not only monumental feats of construction and military organization, but a quietly pervasive technological mastery that touched every aspect of daily life and enabled the endurance of an empire unraveled in history. Rome's public entertainment, festivals, and spectacles were more than diversions. They were technological and logistical masterpieces that reflected the empire's ability to coordinate resources, labor, and engineering on an unprecedented scale. While modern audiences often marvel at the Colosseum and gladiatorial games, the reality is that these spectacles were underpinned by sophisticated planning, mechanics, and material innovation that ensured safety, spectacle, and efficiency. These public entertainments reveal how Roman technology extended beyond military, infrastructure, or industrial achievements, permeating culture, society, and the orchestration of mass events. The Colosseum itself was a marvel of integrated technology. Constructed with concrete, stone, and brick, it incorporated arches, vaults, and radial staircases to support the weight of tens of thousands of spectators. Seating was arranged to optimize sightlines, airflow, and access, demonstrating empirical understanding of crowd dynamics. Subterranean passages, elevators, and trapdoors allowed the movement of animals, scenery, and performers with surprising speed and precision. Complex pulley systems, operated by teams of laborers, could raise cages of wild animals or scenery platforms into position within moments. Engineers calculated loads, mechanical advantage, and timing with precision, creating a spectacle that combined theater, sport, and raw engineering ingenuity. Hypogeme, the underground network beneath the arena, exemplified Roman problem-solving. Multiple levels of tunnels, cages, and lifts enabled animals, gladiators, and props to appear seamlessly in the arena. Water channels could flood sections of the floor to stage naval reenactments, while trapdoors allowed sudden surprises that thrilled the audience. Managing these operations required synchronization, structural integrity, and mechanical reliability, transforming the Colosseum into a dynamic, multifunctional stage. Modern engineers still study these mechanisms to understand how Romans achieved such precision without electricity or automated machinery. Amphitheaters across the empire followed similar principles. While smaller in scale, they incorporated advanced design to manage crowds, acoustics, and structural load. Radial staircases, vomitoria, and tiered seating allowed thousands of spectators to enter and exit efficiently, minimizing bottlenecks and potential hazards. Understanding human movement, weight distribution, and material behavior was critical to safety and durability. Each amphitheater was both an architectural and engineering achievement, where aesthetics, function, and social purpose converged. Public games and festivals required logistical mastery. Food, water, and seating had to be provided for massive crowds. Temporary structures, platforms, and stands were constructed, sometimes in coordination with permanent buildings. Timing of events, sequencing of spectacles, and management of participants demanded meticulous planning. Supply chains ensured that gladiators had weapons, animals were transported safely, and props were ready at the right moment. These operations illustrate the empire's capacity to orchestrate complex, multi-domain activities with predictable outcomes. A technological achievement in administration as much as engineering.